Okay, so let's get back to our discussion on direct simulation of the receptivity problem to free stream excitation. This was the conceptual model that we are looking at. A boundary layer developing over a flat plate is being excited by a train of vortices moving at a constant height with constant speed, and the strength being same. Since it's a train of vortex in front of a solid wall, we need the image system. That's what we said. We went and did all kinds of things. We looked at what kind of excitation this creates. So these are your u infinity and v infinity that is created on the top of the computational domain. And you can see that u infinity has a kind of a delta function like structure around the location of individual vortex. At the location of the vortex, you have a peak and it just simply tapers off on either side. Whereas the v infinity has a feature of like a derivative of a delta function, right? That's your graphical representation of a derivative of a delta function. So that's what we're seeing there. Now we actually looked at the corresponding Fourier transform, Fourier Laplace transform, and we find that the Fourier Laplace transform for the streamwise component of velocity has an amplitude of order 1, whereas this is the Fourier amplitude transform of v component of velocity is of the order of 18 to 20. So this disparity in the spectrum of u infinity and v infinity helps us understanding the problems that we have looked at. We called two classes of problem. One is the pure convection problem and there is a bypass problem. And we figure out that the amplitude of the wall equivalent wall excitation as given by the pure convection problem divided by the bypass problem is given by this. And we can see that y is literally large. This ratio is literally small. So this can be neglected in comparison to 1 plus alpha y. Despite the fact that y is large, alphas are still very small. We know we are looking at asymptotic solution. We also do not know what happens to those free stream mode at the wall, right? This is the inviscid path. So what you notice that these two are essentially nothing but events occurring due to whether you are looking at inviscid vortex in the free stream or viscous vortex. That's what phi PC and phi BP stands for. This is corresponding to inviscid vortex. This is corresponding to it. And one notes that the inviscid vortex actually plays a lesser role, and that's what we can see very clearly, because your inviscid vortex corresponds to c equal to 1. That means the vortex is moving at a speed of u infinity, and that line corresponds to here in the RE omega naught plane, and that is so far out of the neutral loop. So you would know it's a very stable. So it does simply play little or no role at all in exciting a response field. Okay, so that is one thing. We also noted there are some other distinguishing feature of free stream excitation. For example, here the disturbances have to be tracked along c equal to constant line, because that's the speed at which the vortices are moving in the free stream. And the c equal to constant line looks like this. And this very clearly shows that unlike your monochromatic wall excitation, where you would have different frequency results corresponds to different rays originating from 0, 0. And you can see for even for low frequencies, it does have a significant stretch. But if you look at the corresponding c equal to constant, it enters probably later, but it leaves the unstable region much later. So that means that you have a longer stretch of instability. And since it also visits in the center part of this neutral curve, that's where your maximum growth rates are. So this particular route of creating instability by viscous vortices moving in the free stream is a very, very potent one. And since this creates wave packets and not wave, we went with the crowd and we called it a bypass mode, but it is still, the constituents are still the Tolman twisting waves. So, we are getting a wave packet constituting of many, many TS waves. So, that is what we should be looking at, and what we do is we go ahead with the calculation. Now, as I promised to you that we will have nothing to hold us back. So, we will be solving the Navier-Stokes equation, except the fact that we are looking at the two-dimensional flows. So, let us look at some two-dimensional flows defined by the Navier-Stokes equation in terms of the kinematics. So, the stream function equation is basically the equation that defines kinematically the vorticity, right. That is how we get the equation 12. Whereas, the following equation is the transport equation for the vorticity. So, if I am looking at the vorticity in two-dimensional flow, the vorticity vector is perpendicular to the plane of the flow, and that is what we are getting. Unfortunately, there is a plus sign missing. Please correct it. There is a plus sign missing. This is the diffusion operator. These are those convection terms. This is the local acceleration term. What you notice that this is the form of the Navier-Stokes equation, and what happens is the way this equation is written, you can notice that we have split the total variable into two parts. One is the basic part, which we indicate by subscript b. So, ub is the streamwise velocity of the basic flow or the equilibrium flow. Vb is the wall normal component of the basic flow, and omega b is the equilibrium vorticity distribution. So, this omega that you are seeing here is nothing but your disturbance vorticity without any subscript, and this psi is also without any subscript. So, that is also your disturbance stream function. So, we can do this calculation. We only note that this equilibrium flow, we can take it up as the Blasius solution. We can compute it, we can take it also like that. Now, what we do is the following. We have a domain. We have a computational domain that we defined, like we have a plate like this, and we have a box like this, and on the side we have a buffer domain here, and those vortices are here going in this direction, maintaining constant strength and constant height. And what we do is, of course, well, let me get you a better drawing. It looks tilted and wrong. So, let me get you a better quality sketch here. Okay. So, this is the buffer domain, and what kind of spacing that you would require? Well, this will create some kind of a vortices, and we have seen what kind of disturbances this impose on this top wall. In fact, we know that a similar footprint also will be seen here below. So, we will be getting some kind of a packets immediately under each vortices, right. That is what we are going to see. If we are going to see that, so in the progression of that packet, we would not like to have anything other than uniform spacing in the streamwise direction, because there is no preference in the x direction. Because if I have a grid So, the same at that point, sometimes the vortex will move past, sometimes it will be free, but we do not want to do a fancy time dependent grid. So, we will use a transform coordinate xi, which is nothing but the x itself. Whereas, in the wall normal direction, we would resort to some kind of a stretching. So, what we are going to do is we are going to take a very limited height, but we are going to stretch it out significantly. So, we fix this y max in the physical plane, and that would correspond to some computational eta max, and these are the control parameters that will define our graded grid in the wall normal direction. So, we will have a finer spacing near the wall, and which will dilate as we go above. Okay, so this is the form of equation that we actually would be solving for the disturbance quantity. There are certain things that we would like to note here. For example, what we note from the boundary layer property of viscous flows, that the streamwise diffusion is weaker than the wall normal diffusion. That factor is used in defining a buffer function b of xi. So, in front of the streamwise diffusion, what we do is we multiply it by a function b. What is this b? The b is like this. So, if I stretch this part, so I could plot b versus say xi here. So, if I have done it like this, so what it does here, it takes the value b equal to 1 here, and then it smoothly brings it down to 0 at the end of the buffer layer. So, it would be something like this. So, this is your b of xi. So, what it does at the end of the computational domain, b is equal to 1. So, we are not tampering with anything. It is only in the buffer layer we are bringing the diffusion further down. So, that is what we are doing. So, that is the function b. In addition, what you also notice that we have multiplied the vorticity diffusion term by another function called BRE. BRE is also a scaled out parameter, which actually what it does, it has a value of almost 1 here at the end of the computational domain, and then it effectively increases the Reynolds number as you come to the end. So, how do you do that? So, you should have a function that grows with xi. So, that is the role of this. So, you can see these two buffer function b of xi and BRE of xi. These were taken from this paper by Liu and Liu and solved for this. So, why are we doing this? Basically, we are aware of the fact that it will create some wave packets, and we do not want this wave packet to go and reflect from the end of the computational domain. So, by multiplying by these two sets of buffer function, we are attenuating the disturbance so much so that at the end of the buffer domain there is nothing to reflect back. That is the whole idea. In doing so, you realize that results inside this buffer domain is unphysical. So, do not try to give any physical meaning to the solution that you generate inside the buffer layer. You should of course have confidence in the result in the main part of the computational domain minus the buffer layer. This is what one does. Show you some results as obtained from the simulation. Okay. Here in the first part I will show you some result where the free stream vortices are moving with the free stream speed. So, that is your pure convection problem. So, this is a pure convection problem we have put in the vortices at an interval of 100 pi, and this x axis that we have plotted here, this is nothing but Re delta star. Okay. So, the x axis that you are seeing there in this figure, that is your Re delta star. That means u infinity delta star over nu. So, we have computed in a domain which probably starts off around 160 or so and goes on till 2000 Re delta star. What do we know about this axis? We know that pure monochromatic TS waves, unstable waves, will not be created below 520. So, here we have taken a domain which actually spans across from a subcritical to a significantly supercritical range. And you see, in the free stream we had vortices at an interval of 100 pi. So, at t equal to 0, this is the solution. So, you see at the foot of each of the vortex in the free stream, we get some kind of a peak. Okay. And at t equal to 100, what happens? That same disturbances actually decay, because we have seen that neutral curve c equal to 1 corresponds to a very decayed solution, and that is what you are seeing. This peak is coming down. We have also seen that it is a periodic excitation. If it is a periodic excitation, then I will have the excitation in terms of multiple frequencies. So, what happens is, I do get with time, I am going to see that if I have a peak corresponding to omega naught, I will also have a secondary peak corresponding to 2 omega naught and 3 omega naught. That is what you are seeing. The secondary tertiary peaks are coming up. So, this is a very interesting thing. You have created a perfectly steady excitation, and what you are seeing is a typically unsteady solution. So, this is one way of creating unsteadiness in a flow by steady disturbance field, right. That is one thing you see. One more thing also, you notice that if you have looked at what was the scenario at t equal to 0, that was corresponding to particular wave number, because the disturbances were like that. But if you look at the corresponding response field, it is getting richer and richer as you go to larger and larger time. What is happening though? What is happening though here, that you may have started off with one type of excitation band, but at later time the band is going to get filled up. So, why is it happening? It is happening because of dispersion, because different wave number components are moving at different speed, and because of this we are noticing one thing, that your energy spectrum can get filled up due to dispersion. This is significantly different than what we have learned when we talked about Kolmogorov's mechanism, right, cascade, where due to nonlinearity we actually transfer energy from low k to high k. But here what is happening is, it is a linear mechanism. I mean, as you have seen, I have shown you those neutral curves, and all this different modes are coming because of linear instability itself. And that linear mechanism itself is creating a band filling operation. So, this is something not many people appreciated before, but hopefully now you can see. I will come back to this case once again somewhat later, because this is an interesting thing, because we talked about what if it is a free stream excitation, then what should we have? We should have also both upstream and downstream. So, looking at it can we say whether it is going upstream or downstream? Can we say anything about it? It looks like as if it's going downstream. So where is the catch? Huh? We have to check the group velocity of what? See, you have to realize one thing, that what we are seeing here is a disturbance case very much inside the boundary layer, because this portrait that I am showing you here is happening at y equal to 0.3 delta star. So this is somewhere close to your inner maximum, right, for your pure TS wave. So if you look at it, the disturbances are of course going like this. You can, that's why purposely we have drawn in this manner. So if I join the peak, then it looks like this. So that gives you some value of C. Is that C corresponding to the imposed C? Imposed C is going in this downstream direction at a particular value, and that is u infinity 1. So if C is going to be 1 in this xt plane, what that line should have been? 45 degrees. You look at these peaks. Are these 45 degrees or more than 45 degrees? More than 45 degrees. So what is happening? The disturbances are actually going upstream. So you have to understand this upstream and downstream business. There is no absolute reference. You have to talk about with respect to the input. The input is going faster. The output is going in the upstream direction with respect to that. We'll do a little bit of accounting on this. So give me a little time. We'll come back to this issue again. Now, this is a case where we are looking at some free stream periodic excitation, but this is that bypass mode where the speed of propagation is not u infinity but 0.3. And if you recall, I drew that neutral curve. C equal to 0.3 would be the case where the disturbance will enter inside the neutral curve and stay for a long time. So that's the reason that we chose this. And we are showing you the result at two heights. I think one of the height corresponds to I'll send you this PPT material. One of the height, the top one is at 0.3 delta star, and the bottom frame is at 1.5 delta star. So this is like corresponding to your so-called inner and outer maximum, right? So we can see that. What you also notice that these are the traces given as a function of time. So different curve corresponds to different time increasing in this particular manner. And what do we see? That if I look at the amplitude is actually increasing with y. It's ought to be naturally, isn't it? Because we are creating a free stream excitation, so we should have the free stream modes that grows with y, and that's what you are seeing. And what you are seeing is a very remarkably interesting case, because at t equal to 0, it was virtually like flat. Of course, those small bumps are there, but in the earlier case, I actually extended the y scale to show you the bump, which later on decayed. But here is a case at t equal to 0 itself, I put it in a scale so much so that I could fit in the later solutions. And as you can see, with time increasing, the amplitude is growing. So this is one nice example of free stream excitation case, and you also are noticing the same phenomenon of dispersion. You are not going to see a single peak. Even here, you may barely imagine that there is a significant single peak, but there is actually a secondary peak which is running slightly ahead of it. At later time, you can see that very clearly. It's breaking up into a crest and a trough, and that goes on, and again you can see that they are going at a dissimilar rate. So, this kind of opens up. Okay. So, this is something that we did in 2D by solving Navier-Stokes equation, and we did do this particular well designed case where we could see that. Now, we are talking about the propagation of this response field in the upstream direction, right. So, if I talk about c equal to 1, and if I talk about a as 100 pi, then omega naught works out to 0.02. So, what I have done here, I have shown you a plot of the group velocity here versus the circular frequency, and 0.02 is here. So, if I go up, I see that these are all negative Vg. These are all negative Vg. This is 0, this is -2. And if I look at it here, this is somewhere here about 0.6 or thereabout. So, what is going to happen? That if I now excite a system with this omega naught, this train of vortices, the fundamental is going to go at about 0.6 with respect to the input. Do not think in terms of inertial frame. This is important for us to know. What happens to is superharmonic 0.04, that moves even faster, because you see this is the magnitude increasing from 0 to 2, and 0.4 is here, 0.6 is here, 0.8 is here, and so on and so forth. So, we can see that. But what you notice that in the previous solution that I showed you, there was this predominantly 2 or 3 such modes. That's what you are seeing. The one that you can see is this. This is the primary mode. The secondary mode is the one that is upstream of it, because it is going in the upstream direction at a higher speed. So, that is why it fills up. So, you know, I told you that in one of the meetings I met Dr. Kendall. He did a similar such experiment way back in 80s. His experiment was like this. So, take a tunnel. So, tunnel floor could be conceived of supporting a shear layer, and then what he did was he had a support here, and in that support he put in kind of 2 cylinders, and this thing was rotated. So, it was gyrating. So, what happens is this thing gyrates, and each time, let us say it comes here, it kind of sheds a vortex. You know, these are non-rotating cylinders. So, it will shed vortex, and then you basically get vortex of, when this vortex is going this way, then you get one set, then again when this one is coming up there you get. So, it is almost like what we are doing. So, we were interested in imposing a space and time scale simultaneously in the problem. That is what we did. Later on I just figured out that this experiment was done by Professor Kendall, Dr. Kendall, and he also noted that there is a peak in his solution, that when this RPM was synchronized in such a way that this goes at a speed of roughly 0.26 or something, he saw a very massive response inside the tunnel. So, we did discuss this, and he was very happy to see that we could explain it in terms of simple linear theory. Yeah, he was not very sure what was causing this, but this is exactly the case. You know, this may look like a very artificial problem, but those of you mechanical engineering background, you know that this is very, very important in turbo machines. What happens in the turbo machines? You have this stator, rotor, multi-stage turbines, and if you are looking at the compressor stage itself, we will not talk about turbine stage. Turbine stage, why we will not talk about? Because that is too contaminated with disturbances due to combustion process in the combustion chamber itself. But if you look at the compressor part and you look at the stator behind a rotor, then the stator is rotating. So, it is going to give out periodic vortices, exactly the same kind of thing. So, instead of a flat plate, you should be talking about a compressor blade and vortices going there. It's exactly like what that was the reason that we actually proposed this model, and we wanted to show the receptivity of shear layer to some kind of a periodically convecting vortices. And you would see identical scenario, and it's quite relevant that if you are looking at an internal flow inside a turbo machine, the vortices, those will be shared from the rotor. They will be essentially viscous vortex. They will not go at c equal to u infinity. They will actually take the bypass route, and there this kind of things can happen. So, keeping the flow inside a turbo machine is a kind of a monumental struggle because of this simple issue. Then of course, you would have all kinds of other sources of disturbances that we are not talking about, like as I told you, in the turbine stage we will have the same issue. There of course, what will happen, your u infinity also will carry lots and lots of noise due to the combustion process. Okay, so we did talk about the role of Vg and how this affects. So, let me just show you a little more about the case. Here we have purposely chosen the case of c equal to 1 and shown the solution at y equal to 1/3 delta star by 3 and y equal to delta star, and shown you snapshots at 4 instances, t equal to 100, t equal to 410, 730 and 1260. So, to begin with, we had the vortex at I think it was at 100 pi interval. So, the first vortex was kept at around 345, and the following one was at 315, then 630 and so on and so forth. So, if you look at t equal to 100, where would you see the free stream vortex be? That would have gone 100 to the right, but at the same time the response field is going at 0.6. So, you can find out. So, it is basically then going to the right at 1 minus 0.6, so about 0.4. So, if you do that, you can really see these peaks correspond to that. Okay. So, that is what you are seeing. Okay. In addition, of course, you do also get to see some kind of a downstream propagating modes, right. Those downstream propagating modes go at what speed? Depends on what we have seen before, depending on what is the local RE delta star, and we have seen the TS waves go at something like well, in this case of course there won't be any TS wave going because c equal to u infinity, you will only have those damped modes. And if you see that maximum damped mode was going at a speed of about 0.82 or something, right. The unstable mode and the second stable mode, I think it was going at around 0.4, 0.45 in that range, but the third mode which existed say for r equal to 1000 was at about 0.85. So, those actually go downstream, and those are the ones that you are seeing little upfront. So, this is one way of interpreting your result, that it is quite complicated, but you can see what is happening, that you have started with a single peak, but because of dispersion they are breaking apart different omega naught. Then this is also breaking apart due to an upstream component and a downstream component, and you can see that graphically goes on with time, and that kind of fills up the whole thing. So, we started off with a very coherent excitation, but here we end up with sort of filling up the whole space. So, this is the story of the pure convection case also can provide the seed of instability in a boundary layer. So, now do you see what I am trying to drive at, that we have done the eigenvalue analysis, and we have seen that if we create a particular length scale and particular time scale, then we can create TS waves. So, what in a sense we are saying, that even though you allow a inviscid vortex to go to begin with, it will be pretty harmless, but with the progress in time you are going to see that it is going to fill up all kinds of length scales. You can take this solution and do an FFT, and you will see that it is quite a wideband phenomena. Question is about the corresponding omega naught. The omega naught also we have seen what can happen, that we are not only creating omega naught, we are creating n omega naught. So, higher frequencies are going to be excited, and those can give rise to your 2D modes. And the solution that you are seeing is from a 2D calculation. So, you are only seeing 2D calculation, but think of the actual experimental scenario. In the experimental scenario, what you are going to see? You are going to see those Klebanov mode, right. This low frequency excitation will make the whole boundary layer breathe up and down. So, you are going to see a very, very complex flow phenomena. So, in a sense, what we are hinting at here is that if we do go ahead and do this sort of calculations, or you do the experiments, transition is virtually inevitable. See, this was supposed to be a very simple case, right. So, here in this table we have given you a proper accounting of what we just now explained for that pure convection case. I told you the vortices are placed at 300, 615, 930, 1245, etc. But there are vortices also upstream of the computational domain. So, I have noted some of them, because at a later time they will move in. So, like the one which is at t equal to 0 at 15 will at a later time will enter the computational domain. And what happens is, so we are writing all those locations starting from a minus 960, minus 645, minus 330, minus 15, 300 and so on and so forth. at t equal to 100, I showed you those 4 frames. Where would we expect the solution to go? I mean the input to go. At an interval of 100, it will go to 400, this will go to 715, but the response that we saw, where did we see the peak? The peak we saw at, instead of 400, we saw at 350, and instead of seeing the peak at 715, we saw at 650. So what does it say? That with respect to the input, the response has moved upstream. And what is that speed? About 0.5. That is what we saw, that Vg versus plot. And here it was supposed to have gone to 85, we see a new peak coming up at 35. So you can basically see this. You can see this, that there is another peak showing up here, which is not here, but that is at 30, and this is your 365, this is at 665, and this matches rather well that what we are talking about. Now, well, anything on this side does not make sense, but the next frame that we showed is at t equal to 410. So now this vortex, which was initially at 300, has gone to 710 in the free stream. The corresponding response field would go at, is seen at 505, and once again you can see what this is. This is roughly around 0.5 Vg, right? At 400 it has gone about there, and this is, instead of it was in the free stream, it is 1025. So if I do it 410 into 0.5, it's about 210. So it's about 205 gap. So that's what it is doing, and this one, which was outside, now it has come to 270. Okay, and this is still on the outside. And now you see what has actually happened at t1 equal to 165, this entered our computational domain. So computational domain is not starting with the leading edge. So it is somewhat later. So that is what we have indicated by this T1 star when these vortices enter the computational domain. Like this third vortex would enter the computational domain at 490. This one would enter at 810. This one would enter at 1120, and so on and so forth. And you can see that this kind of very clearly explains that one kind of response field for pure convection problem. Okay. So what has actually happened? We have finished this particular part. I will now show you something. Let me, no, this is not the thing that I am looking for. This is something that I want to share with you now. So, you know, I mean, we have, as time progressed, starting from simple linear stability theory to what I just now discussed, shows that even under the linear theory ambit, we can see so many complex things happening. We can see that pure monochromatic excitation as it was done in Schubart's-Kramstad experiment. We have also seen the free stream excitation by simple train of vortices going outside, and that can lead to very complex things, and which we called a bypass transition. But you know, in actual fluid flow, it so happens that on many occasions linear theory do not even work. linear theory do not work. Classical example is the pipe flow we discussed. If I do linear stability theory for pipe flow, it is shown to be completely stable. The co-ed flow, the shear driven flow, that if I have flow between two parallel plates, top plate moving, bottom plate stationary, that flow profile is a linear profile, and you can do the stability analysis and you will see that it is stable. The other example is look at flow inside a rectangular channel, which is called the Poisson flow. The Poisson flow, the velocity profile is parabolic. You do a linear stability analysis, and what you notice is that the critical Reynolds number is about 5,700, whereas that flow is known to become unstable even as low as a Reynolds number of 1,000. So, there are any number of examples where people see that you could have instability, but the linear theory is not so good. So, people researchers have worried about it, and one of the leading scientists in this particular area was Professor Markovin. He coined this term called bypass transition. And what he meant that there are all these nice lab experiments where we demonstrate Tolman-Schlichting waves, but there are many flow situations where Tolman-Schlichting waves are not at all relevant, and they are undergoing transition due to some other mechanisms. So, all these other mechanisms taken together, he coined it as the bypass mechanism. This is something that we have seen, that if I go to a wind tunnel and see what is happening inside the tunnel, it is a so called natural transition, and this is the result again I am showing you again, taken from that Schubauer-Scramstad paper. If I look at it about 7 feet from the leading edge of the plate, then what we find that this is the kind of response field that we see. It is measured with a hot wire probe, and what you notice is a significant lack of monochromatic disturbances. You see what has happened, the initial objection to linear theory was so strong. Lot of researchers spent a lot of effort to first establish the linear theory. That is what Schubauer-Scramstad experiment was all about. But when you look at real flow, this is what actually happens. You do not see monochromatic wave, do you? You do not see at all. You see the sequence of events going like this, but then what you see also, progression of the growth of the disturbances with streamwise distance. And these are the magnifications with which these solutions are shown. This is 4 times magnified, this is 3 times magnified. By the time we are here, we are only magnifying 2 times. So, you can see that it is growing, and it is not at all a monochromatic wave, and then all of a sudden it has this kind of peaks. And when it does become turbulent, that is characterized by very rapid fluctuations, which we all know what happens. This could be even a transitional flow. Nobody is saying it is fully turbulent flow. This could still be transitional flows. And let me add to what I already said, that this kind of scenario that is we are seeing here, it is because maybe the background disturbance was rich in harmonic content. It was not a single frequency, it has a multiple frequency, and those responses due to different frequencies have to be added together, and this is the sum and substance that you are seeing. So, I will show you a few days later that what happens when we excite a boundary layer with a strip that may be still going, at a single frequency, but because of this finite width, I would create waves of different wavelength. Why? Because of the finite width, my local Re delta star is also not a single number, it is a band. So, each point works as a source, and each point, because they are a different Re delta star, for the same omega naught will create different alpha r and different alpha I, and I have to sum it all up. So, this normal mode analysis does not tell you what is the relative weight of different harmonic content, right. This is same omega naught, but different source point will have different thing. If you recall that we did all kinds of things, that Gaussian and the strip vibration, then we simultaneous blowing suction strip. So, we do not know in a stability framework what weightage to give to each position, but what we could do is, even if we consider that it is a kind of a white noise type of thing, that every point is weighted equally and I add them up, I actually end up getting pictures of this kind of various hues. I will show you some such calculations which we have reported ourselves. But what happens is, primary instability is just one of the thing. Primary instability is just the beginning of the story. So, now what you have? You have the basic equilibrium flow plus a disturbance. Now, what one should do naturally? One should naturally also study the stability of this unsteady flow. See, your basic flow could have been perfectly steady, but because of instability I have got because of primary instability, now I have the basic steady flow plus a unsteadiness due to this primary instability. What prevents us from going further? And this is exactly what Landau suggested. Landau suggested that after you have gotten the primarily unstable flow, you should study the stability of this compound flow. That is a combination of a basic flow plus a. If you look at it from the point of view of Schumacher-Kramstad experiment, then we are talking about what? We are talking about a basic time independent flow plus a periodic flow, because we have created a monochromatic wave. There is some such theory that was developed by mathematicians. This is what is called as a Floquet theory. In Floquet theory, we study the stability of an equilibrium flow which is periodic, and we can do that. So, Landau actually suggested that. Landau said that is the route with which we go to complete turbulent flow stage, that we have this sequence of instabilities coming. Later on in 70s and 80s, two mathematicians by name Ruel and Taken came. They said that you do not need to have a very large number of such instabilities. They said maybe 3 or 4 such instabilities are good enough. That is called the Ruel-Taken scenario. So, we are coming from the primary instability to the Landau scenario, but then Ruel-Taken came. Then they said you do not have to go for very large number of this thing, you just simply have 3 or 4 such bifurcations and you are done. You will get a totally chaotic flow. So, I think that is where I will stop today, but in the next class we talk about some of this other possible routes of transition and see what happens. So, for the time being we will keep the Tolman-Schlichting mode in the back burner and we will look for other modes.